When removing a node with two children, this is the hardest scenario possible since everyone in the roots subtree is affected. We have to replace and not actually delete the data in the target node. Now, the target node meaning the one that we're about to delete. The weird part is that we're going to replace it with the smallest value found in the right subtree using a function that's actually already there called find min. Now remember, find min, all it does is go as far left as possible to find our next minimum value. Now we still have to travel to the target first to delete it. We also, in finding and removing the minimum node, we also have to do the remove all over again there too. So this is actually recursive in setup when we are replacing or removing a node with two kids. Here's where things get even uglier, is that when you're online, you may have some authors that grab the greatest value from the left side. So in the original tree that I have for you, there's two different types of replacements that we can use. We can do the left side replacement that looks from the target node, which is going to be 25. It's going to look at the left side and find the maximum value and then move that 15 into the 25 spot. Whereas the right side, the one I just described, it's going to throw you the right subtree and ask you to find the minimum most value, which is going to be all the way onto the left-hand side. Now, do both of them work out? And that question is it still a binary search tree after we do either one of the side replacements? And the answer is yes, if we do it correctly, of course. But in either case, both of them do it correctly. Now, is there one that's preferred over the other? No, not really. In actuality, we have to be careful because if we keep deleting from one side all the time, well, we may end up having a very lopsided tree if we have a lot of deletions. So you'll even see some code that does a randomizer to pick which side we'll eventually get the min or maximum from just to do the replacement of. Now, there's no way of really showing this in any pretty way, so I'm going to show the C++ and then the Java code after that. But again, notice the first part of this entire algorithm is just finding the darn thing. The other part is then figuring out, once we've found it, if it has two children, one children, and then no children. So be very, very careful about the overall setup with that as well. Notice this is a recursive function because, well, again, if you remove one spot, you may have to pull from another. The other neat part about this is within this is, again, if it has two children, you'll notice we have the find min function, and that returns our newest value into that location. So notice that find min returns a value that's going to be now reset to that current element or node that it is located in. And then it does the remove just to figure out where that element is, well, after that. So this is a very convoluted remove function that's very complicated, so be very, very careful about this. Now, if you also notice under the one child item is that we actually create a temporary binary node, set the value, and then we have T reconnect it either from the left or from the right side that originally was from before. So a lot of stuff going on here. Now I'm switching to the Java side. And notice for you Java people, it's exactly the same setup. First we got to find the sucker. Then we have, has two children or one child. It really is the same idea. There's my find min again, which is going to return a value. There's my remove, going to return a value to, well, get the overall setup when we have two children. It's recursive, same exact scenario, just in different language. Make sure you hit pause somewhere in here to take a real good look at the code and notice all the comments that I try to put in there as well to really help you out with this.